All right, so hello everybody. Welcome to another lecture of 165. And so today we're going to continue our discussion about modern databases and the way they handle storage and indexing. So last week we covered sort of the basis, why there is a need for an indexing. We looked at potential, what the tree structure or hierarchical structure look like, and what are their capabilities in terms of they can do equality search, they can do ranges, but then they're more complex to handle because they have this more elaborate structure. Then we looked at hashing, which is much more flatter kind of structure, much more simpler in terms of implementation, especially like a lock or latch-free style implementation. But then they have a shortcoming of not be able to support range queries. So we looked at an extension of that. In particular, we looked at rhash that allows us to do range queries on hash structure. So that's the kind of where we left off last week. And so today we're gonna kind of now look at the storage layout and how does the indexes are built on top of the storage. So that's where we left off, database storage layout. So the most basic thing, and this is going to be actually really good for your milestone as well too. So the basic idea here is that the data are stored as records. Records are stored in pages, and there are different kind of layouts of how we're going to store these pages and records. Well, one simple way is that you can think of just a page as an array of bytes, and then each record itself also as an array of bytes, and a page could be a list of arrays, one array for each record. I mean, just conceptually, the entire thing could just be just an array of bytes, and then you can break it into maybe equal size slices. For example, if you say each record has 100 bytes and my pages contain 4,000 bytes, then I can store 40 records on my page. Does that make sense? So very basic idea is that I have a single page and it's called a row-based layout, and I'll just basically just lay out every row one after another until my page is filled. And once the page is filled, then I simply go to the next page. Any question? So that's our traditional way of storing the data. We could also consider a different way of doing it, which is not row-based, and this is column-based. And so the way the column-based works is that instead of having each page contain the entirety of the record, each page only contains one field or one attribute of the record. Again, we talked about what we're dealing with is tables. Tables are rows and columns. On the left-hand side, when we have the row-based model, essentially each tables consist of a set of pages, and in each page, the entire record with all of its columns are present. But in a column-based way, each page only contains a single column. So if our table contains, our student table, for example, contains name, age, and major, then on the row base, each record will have the value for all those three attributes or all those three columns. But in the column base, we will have three different pages. In one, we'll just put all the names. In one, we only put all the ages. And in one, we put all the majors. And once these pages are filled, we can simply allocate more pages. And so you keep adding more and more and more pages as needed. But what's interesting in the column base is that if you kind of start from the top, the third entry of every column correspond to the same record. So the third entry is Alice, the third entry of its age is 21, and the third entry of it, the major of it is computer science. In the other form, in the row base, the third entry of the first page contain the entire record. So and that's the kind of the two basic fundamental way of storing the data. You could have a row-based, or you could have it column-based. Any questions so far? And for LSTOR and for the milestone that we're going to look at, we are going to adopt this columnar format. We're not going to have a row-based layout. So that's the design. That's a major design choice in terms of the storage architecture of LSTOR. So now, kind of let's to understand. So what's the difference, or why would I care one over another? What are the key attributes? Perhaps does anybody kind of just by looking at these, can you notice anything special, or perhaps anything unique, or any particular advantage or disadvantages of these two designs?
You can probably fetch a whole row a lot easier in a row-based layout.
Absolutely, absolutely. I can, let's say if I know exactly where my record is, in one shot, I could get all those attributes. But so go on.
Oh, I was going to say, if you wanted to calculate like an average of all the ages, the column would probably be better.
Yes, and why? I mean, you're right on, but why?
All the ages are in the same place.
All the ages on the same place, and there's one more reason.
They're stored in memory sequentially.
They are stored in sequentially, and they're in the same page. One more.
They're all the same data type?
That's really important. They're the same data types. When there's the same data type, you can actually do compression much more effectively, because compression is about how sort of the distribution of the data. And if the distribution of the data is it's much more unified in terms of the value types, then the opportunity for compression goes up. When it becomes too diverse of all different, and they cover too much of the space, then it's much harder to bring that footprint lower. So compression substantially gets improved. Sometimes you get a factor of 10 improvement on compression when you move from row-based to column-based. So that's one of the fundamental benefits of a column-based. But there's still one more.
Sorry, I don't understand. What is compression again?
Compression is that, so like compressing the data. So as opposed to, so what happens is that each pages, often you may not just store the raw data, you may compress it and then store the compressed data because you want to store less. You reduce your storage cost. But if I'm kind of trying to compress different kinds of fields which each have different data distribution, then there's too much variance on the same page. So the compression becomes less effective. But if I have a data type like age, that let's say everybody's 21. So then I just need a single symbol, and I can just use one bit symbol to say 21 is the most common repeated element. Instead of just writing 21 every time, I'm going to say a single bit, like value 1, represent 21. And every time the 21 appears, I'll just put one bit. So you can get a huge compression. That's just like a very simple sort of idea of compression, but there's a lot more sophisticated way of compressing. But when the data are more uniform, there's less variance, then the compression becomes more and more effective. So in this column base, the compression is a lot more effective, and that's really important. Still one more left. We're kind of getting very close to it, but there's still one more left.
Is it because if you want to take the average of all ages, you can just get the age table instead of having to get the whole table?
Exactly. So if you wanted to go to the average, I don't need to read the columns that I'm not interested in. I don't need to read Alice and Bob, and I don't need to read the major. All I need to read is the age. So that means I'm going to read a lot less data. That means I'm going to bring a lot less data from disk to memory and from memory to the processor. So if I now look at the entire storage hierarchy, the flow of the data on my storage hierarchy all the way to the processor is now substantially less. It's substantially less because I only read exactly what I need. It's going to be more compressed, and it is going to be more compressed, and it's also going to be sequential. That was another reason, that was another important, that was mentioned as well too, is that they all could potentially be contiguous, sort of right next to each other, meaning I don't need to do random accesses. I could potentially do all sequential accesses. And sequential accesses on every device, or almost every single device, will give you better better performance profile than if we were doing random accesses. So that's why it makes the column oriented layout a much more it becomes much more performant, and you could potentially get hundreds of 100x improvement on performance. Of course, there was an important element that was also mentioned for the row base. If I'm just interested in reading a single record, or if I'm interested into modifying a single record, then the row base is much more efficient. So again, that's coming back to this notion of trade-off that I kind of had mentioned. It's really the database system is really built upon understanding and navigating this trade-off space. So if I only need to access one or two records, whether I need versus accessing hundreds of records. So if I'm only accessing one or two records, then the row-based one could be the preferred one. If I'm accessing hundreds of records and I'm only interested in a subset of that, then obviously the column oriented will be much more beneficial. So in general, analytical type of workload, when I need to do analysis, the column oriented is much more effective. If I'm trying to do just a transactional workload, like just building a shopping cart or doing purchases in retail, then the row-based tend to be more effective. And again, so that's the key trade-off. And one of the principle of the L store is that there's no way when it comes to the write that I can outperform the row base, and there's no way that I'm going to reach the 100x performance benefit of the column store. So let's start with the column store as a baseline and say I'm going to try to get a 100x improvement in analytics. I'm not going to try to outperform the row base in terms of its performance of read and write of a single record, but I want to try to get as close as possible. So with a small compromise on the write throughput, potentially get a 100x improvement on the reads. And so that's one of the basic design. And so there was a question is that also over the weekend I received is that sort of the relationship of HTAP and LStore is that HTAP is really that unification of doing an analytics and transaction. And one step of this unification in the sort of the process of the LStore, and kind of we look at all components of the data, but at the storage level, that's the first one, is that it allows you get the benefits of the columnar that could potentially get you the compression, that potentially only need to read the data that is necessary for the analysis that you want to run. You don't have to, if you want to do an average on age, you don't need to read the name. And so that's having that plus without compromising on write. And so those are kind of forthcoming as we get into the core of the L store in the coming weeks. So any question on this?
Yeah, I had a question.
Professor?
Sure. Yes.
Go ahead.
Yeah, so it looks like in the column-based layout, the number of pages you have is basically equal to the number of keys you have. And then in the row-based one, it's basically dependent on the number of different students you have in this example. Is that accurate?
So let's kind of make sure that we use terminology the same because otherwise we could get a little bit confused. So key, these are columns or attributes, they're not keys. So key of a relation is a particular column or a set of columns that uniquely identifies a record. So for example, if name was unique, that means no other student had the name Alice, then Alice could have been a key. Oftentimes that's not the case, so we have a student number. So usually we have a student column, a column called student number, and student number is the key of the relation because the key uniquely identifies a particular record. So now in terms of kind of what you pointed out, which is important, is in the row-based one, we're putting the entire record into the one page. And once this page is filled, we could just simply go to the next page, start filling the second page. Once this page is filled, we simply go to the next page. So you could say it's just the total size of my data divided by the size of each page will give you the number of pages. So pretty simple calculation. I'm not going to worry about compression for now. We're not even going to worry about for our assignment, at least not as a requirement. It could be a bonus. But now, in terms of in the columnar one, is that here if all our data fit in one page, in the columnar one, we're probably going to have at least 3 pages because we're going to have one page for each column. So the number of pages, it's going to be dependent on the number of columns plus how much data it involves in each column. So if so that's the way that it's going to look like. So minimum number of pages here is going to be the number of columns, but how many pages for each column? Well, again, that depends how much data it is for that column. It could be for name, it could take 3 pages to store the same number of records. For age, maybe the size of age is smaller, so it may take 1 or 2 pages. For major, maybe it's also small, maybe it's just a 2-bit value or a 2-character, maybe that only takes 1 page. But again, that's kind of really dependent on how much data exists for that particular column.
Got it. Thank you.
You're very welcome. Again, that's an important question. So they don't have to these ones. So the third element in each of them going to correspond to the same record, but it is possible that name is 10 pages long and ages is only 2 pages. There's only 2 pages of for age. And for the assignment, we kind of simplify it. We kind of make all the columns of the same size in terms of the bytes, so there is more alignment. So all of them will have the same number of pages. So that's kind of one simplification that we will do. We also do fixed size. So each field is of fixed size. And here we kind of assume fixed size. And fixed size is easy because if I need to look at the 4th element, and all I need to do is just I know what's the size of each record, and then if the size of each record is 100 bytes, then I know the 4th element start at 300, goes all the way to 400. It's easy to compute that. But if the size were kind of variable, then it's not that easy. We'll kind of have to do a bit of a calculation to figure out where is the starting point of that record. And we're going to look at that next week as next lecture. Any other question? Again, this is fundamental because, yeah, go on, yeah.
Sorry, I just had one more question. So again, the advantages of the column-based, it's compressible, it's sequential, it's less rating for certain queries. Was there a 4th one?
So So one is you only look at the data that you need. You're going to minimize the data. If you only interested in age, you're only going to read the age data. And it compressed better because each page contains data of same type and same domain, so it compresses better. And the sequential part, that one it's not a clear-cut one. I mean, there's certain condition has to be met. So, but the key idea one is you only read what you need, you get a better compression, and yeah. So those are I would say those are the two main ones.
Okay, thank you.
And in terms of sequential, it now comes to the order, the ordering of these. How are they sorted? How are they constructed? And so there's a bunch of other things come into play that may affect that sequential axis of it. But the other thing that you could think is that since I can, in one page, I can fit more data if I'm only looking at age. So I could, if in one page, I could have the record, maintain only 4 records. In the column one, for example, I could maintain 8 records of age. So I know at least 8 records I can read sequentially in one page, versus in the other one, well, there were 4 sequential record or 5 sequential record that were fit in a page. And there are some, but now going across boundary from one page to the next, that's a different question. And whether they are actually sorted or not, that also affects that sequential axis. Because if the column is not sorted, well, you still have to access the entire data. So it gets a little more complicated there. So now the question is, if I wanted to be able to search for age 21 and 24, and well, I can have an index structure as we talked about, and the index is built on top of, it could be built on top of my row base or column base, and from the index 21, it points me to the right record. From 23, it points me to the right record, and the 24, it also points me to the record that maintains 23 and 24. And the way the index usually works, it has a key, and then it has what is called a record identifier. And the record identifier is essentially a pointer that points me to the page that holds the record. And the record identifier could maintain, so inside the record identifier, which you think of it as an integer, part of that integer could be the page number, and part of that integer could be the slot in the page which contain that record. So given a read, I can always find physically where the record is on my database. And when in databases, the notion of read, that record identifier is sort of essential. We always, when you are referred to a record, so we'll find that record from its read. And so the reads are stored in indexes and in other places as well, in our page directory, and kind of we're going to use that the concept of reads quite a bit in our conversation. So now with the row base, if I have an index, I can kind of quickly find these. And if there's only few elements, a few records that matches my search criteria, then I only need to look at few pages, and it's I guess the index could be effective in that case. But if I need to access on my column base, as we talked about before, is that I could just scan kind of the age record and find all the students that satisfy that the range condition of 21, 24. Of course, I could have also used indexes to find the relevant record. This read could also be pointing to the column. It doesn't mean that the index cannot point to a column. It works either way. But the question is, if there's too many rows that matches this, then maybe just doing a sequential scan would be faster. And if I need to do a sequential scan, well, maybe better to, well, not maybe, definitely would be better to do that sequential scan on column base, because, well, I'm gonna, for all the reasons that we listed it, I only need to read the age, and I can sort of limit the amount of the data that needs to be read. So that's the kind of sort of optimization question that one can ask between read and write. And then the kind of question is, if you remember earlier last week, we talked about the importance of having a way of quickly retrieving the data. Then we said, kind of raise the question is that, well, how do we improve it? We can kind of bring some structure, and then we kind of add some hierarchical structure, and then we have these like tree structure. They're very effective, but then we said, well, tree structure are kind of a little bit too expensive to program, too expensive to maintain. Then maybe try to flatten the structure and kind of ask, can we just use hash tables? And then we said, okay, hash tables can't really do range queries, and can we slightly modify it to now be able to do range query with hash table? Now we're saying, okay, our scan can be done even faster because we have column store, and now we kind of reversing the path from promoting having an indexes. Now we go back to the other direction, saying, well, if I can do my scan really fast, I can read the data sequentially very fast, then maybe I don't need an index. So kind of completely going the opposite direction. And again, for some workload, it may make sense that you don't really need an index as long as, and so there are interesting parameters one you can look at. So traditionally, if you wanted to read the data and you said you need to read about 5% of the data, or that your query is going to return 5% of the data, if it's less than 5%, it's always more effective to use an index. If what you're returning, it's more than 5% of the data, so more than 5% of the data satisfies the query condition, then it might as well to just do the scan. So this was the old kind of a rule of thumb to decide when is effective to have an index structure. But with the column store and with all the benefits that we mentioned in terms of compression, in terms of reducing and kind of limiting to read to exactly what is needed, that number also has changed. And it's really dependent on the system. So it's not an exact implementation, a particular database. So it's kind of very specific to that. But in sort of recent databases, we'll find, for example, in Oracle or DB2, in the columnar layout, we'll see even if the data that you're looking for, it's only 1% or 1/10%, then only if it's under 1/10%, then it makes sense to look at an index. Otherwise, if anything above 1/10% or 1%, you might as well just do a scan, because the scan has become much, much more efficient because of the reason we discussed. So again, it becomes interesting. But if you are supporting like transaction, and transaction requires updating or reading a single record, then for those cases, of course, or a handful of records, then indexes will always be beneficial. And kind of we're gonna, in our assignment, in our milestone, we will have indexes to improve the speed up of those single read. And we will also have scan operation that we do. And of course, for the scan, we're not going to use index because it's not effective to use index for those as well. So again, we're going to kind of get those experience as well too. Any question? And if my queries, again, just give you another example, if my query was to return me everything larger than 24, then I could just go to 24 with my tree structure and then follow 24 onward. If I had a hash, as we talked about, hash can only do equality, but if you look at sort of R hash that supports range queries, then that's something we can also do with R hash. But of course, something that would have been feasible with regular hash. Again, for your assignment, we will use indexes, and you can use trees, or you can hash or a hash table. We can also go ahead and implement R hash or a variation of that R hash, and that will constitute as bonus. And I kind of noted in the assignment, in every assignment, not only you have the full freedom of kind of the implementation, the design, the architecture, and so forth, but there's also kind of opportunity to gain up to 20% bonus and either creative ideas that you come up with, that's the most encouraging one, or if you learn something in a lecture that is not outside the scope of the assignment, go ahead and kind of implement that, and then you will, depending on the effort, you will get up to 20% bonus for each milestone. Okay. So that's it, I guess, for this part. Any question? So I can now switch to the second half of today's presentation for your assignment. So kind of going back to kind of set the stage again, what we have, database at a high level view, we have the storage, we have indexes, we have the log, and then we have the concurrency protocol, which manages running multiple threads in parallel. Just so the other one is from the database layer. So again, sort of another view of the same architecturally, we have disk management, we have buffer management, file and access method, relational operator, and query optimization. So relational operator could be just get some put. Files and access method is the way about our indexes and about how the files are stored on disk, and the stuff is stored on the disk, and then they need to be brought to memory. And that's the job of the buffer management. So file and access method, this is really assignment milestone 1. We assume everything is in memory, and milestone 2, we assume now we have also disk. So then the data that the indexes and your relations need to be stored on disk. At least your tables and relation has to be on disk, and then they brought into memory with the buffer pool. So that's the second milestone, and the third milestone is about concurrency. So now, in terms of how the disk, as we said, can retrieve the data, we can do random accesses on disk. But of course, if you do sequential access or if you read a set of consecutive pages, it's much cheaper. So this is just at the hardware level. And that's why even in the previous one, we had this conversation. It's important if you can do sequential access, the more sequential access, the higher throughput that we can get from our storage device. Tapes cannot do sequential access. They can only do, they cannot do random accesses. They can only do sequential accesses. So you have to start from the beginning to the end. That's the only way. Of course, they tend to be cheaper and they tend to have a higher density, and it's really for archival purposes. And sometimes you may go, at least in the past, you may go to the bank and say, okay, I want my statement. And if your statement is within the last a year or two, well, they may just pull it up and give it to you right away. But before, if your statement was for 3-4 years ago, then there was a whole different process, and you may have to wait a month or 3 weeks to get that statement. And the reason was, well, they had to go to tapes, and they had to go to other kind of storage to retrieve that. Of course, storage becoming cheaper and cheaper, and banks are relatively don't have much data comparison to what, for example, Google or Facebook are dealing with. So things have changed. But 10-15 years ago, they're still a bit different. So, and then file organization. So how the data is actually stored on the file. Again, one important idea that which I've already mentioned is the record ID, is the RID, which is a reference, an identifier to find a record, and typically contains the page number and the slot ID of where that record is within a page. That's for column, that's for row based. For column based that we're going to work with, it's a little bit more complicated, because as we said, a single record is no longer on a single page. Each column of a record is going to be on a different page. So the RID becomes essentially a more logical. So there must be another mapping layer to be able to figure out for each column of a record in which page and what's the slot ID in that page that particular field is. So it requires a bit of a mapping, but straightforward sort of traditional RID for a record for row base is usually just page ID and the slot ID. And then again, indexes, we talked about, you already know this, that is to find a record efficiently, very effectively. And we talk about search key, and the search key is the key on which we're searching. So if you have an index on age, the search key would be age. But also I mentioned earlier today that a table or a relation may also have a key. And that key is what uniquely identifies that record. So for example, for a student table, the key of the student table could be student ID or could be social security. But the search key, if we have an index on age, then the search key of that index would be age. So the word search key versus key. Key is the key of the relation. Search key is the key used to search. Is for the index. It's essentially the attribute that the index is built on top. And then buffer pool is, as we said, just it allows us to read data or bring data from disk to memory. So that's the role of buffer pool. And it's just another way to think of buffer pool is just a set of pages in memory, and you manage a set of pages in memory. And then there are many alternatives to how do I organize my table. I can just use heap files, just random orders. And the example that I was kind of showing you earlier about the row and column, this is just heap files because I just start, I take a page, I start filling it in my record, it finishes, I go to the next page, then to the next page, then to the next page. Nothing, it's very simple. And so that's random order files. We could also have sorted files, but sorted files is much more difficult because if I have all the data ahead of time, sure, I can sort the data and essentially do a heap files to just lay out all the files and automatically everything will be sorted. But the problem with the sort file is the maintenance of it. So now if I'm inserting new records, I potentially have to reshuffle everything around. So the maintenance of the sorted files, it's not trivial. And indexes, well, again, we talked about, so the way the indexes are structured and the way the pages are added or removed, it also dependent on the structure itself. And we're going to look at that a little bit more. But high level, any questions so far? I'm going to look at a few examples of, especially the last two. Well, the first one we already looked at an example already. So, and again, with indexes, it does actually have the flavor of sorted files because essentially it's, we talked about the trees are essentially sorted. So then reads and writes are much faster. And also indexes could be a way of having sorted files. So one way to implement sorted file is to have an index structure. And I'll give you a little more details on that as well too. So again, index, we've already seen it, so I'm not gonna repeat ourselves, but index is basically a way to speed it up. Index has a key, and that key is the column or a set of column on which the index is built on. So for example, it could be on the name, or it could be on the age, or it could be both. It could be a composite key, meaning the index is on name and age. So again, those are all possibilities. And we also, as we showed in the previous set of slides, is that given a key like the age 21, it points to the actual record that has age 21. So essentially, it has inside the index, we have a key with a set of reds. That's kind of the simplest way of thinking about it. And that's, so now an example of B+ trees is that we have these non-leaf pages, and then we have the leaf pages, which contains the actual data. And if you look at an index entry, so it's the pointer and the key. So for example, key 1, so this could be 25, the second key 35, and this is P, could either be a pointer to the next page in the tree, or this P could actually be the record on a file. It could be a read. So let's look at one more example. So for example, this is 5, and it says all the all the entries in this leaf page has to be less than the 5, and then that's the P0 that I showed in the previous one, the P0 which is the reference. So I have a key. This is everything smaller than 5, and this is the reference that points to that page. This page, everything is less than 13, and this is the reference to this page. Of course, this is one way of doing it, that we say that all the element in this has to be less than 5. The other way of kind of saying that, we could say all the element in this page has to be greater than a 5. So that's kind of a choice. As long as we are consistent on that logic within that data structure, then it's okay. But that's one example of structuring it. So, and on the leaf page, it's basically just a set of entries. And each of these could itself now have pointers. And those pointers could be a set of grids or a single grid, now pointing exactly where into the file the 2 points to, the record that has the value 2 for whatever that column was. So we're not going to go over this. I think this is, you already know how to do a search on a tree. And hash indexes, we kind of talked about it already, and we even went far beyond just the simple hash. We talked about R hash and how do we do range queries. But again, hash is just a collection of those buckets that we talked about. And if there are collision, potentially you could have overflow pages or overflow buckets. And we kind of saw those collision in the last class as well too. And again, given a hash function, you given a search key that you're looking for, then you can figure out which bucket it is. And you may have to look at the overflow buckets, or whenever there's collisions, you kind of potentially have to look at a linked list when you hit that bucket of overflow elements. So any question so far on this hash and the trees? I mean, I suspect most of it is probably material you're kind of familiar by now, so I'm kind of going over it a little bit faster. Okay, again, anytime you have questions, please stop me. So now the question is, what do I store? So I have my search key, and so what do I store in that? So if the search key is H21, what I've showed in the previous slide is that there is a reference pointing to where that record is. So that's one alternative. So I could have my key, this is like H25, and then the rid of the data record with that search key. Or it could be 24. I mean, for every valid key range, there will be this entry, a key and a rid of the data record that has that key. So that's one basic structure. The other one, you could have K and a list of rids. So for example, H25, the rids is from 85 to 95, for example. So a list or a range of keys that have this particular age, for example. So again, that's kind of just a couple of alternatives that we can implement. But the more interesting one is, what if, so it's also often referred to as alternative 1, I guess for a lack of better name, is that instead of with RK to have a rid, have a reference to where the actual record is, we could store the entire record right there and then. So H25, so for the key H25, instead of pointing to where the record 25 is, I can just insert that record entirely right there and then. And so can you think of, so this is an interesting one. So this is also called index organized file. So can you think of why that would be beneficial? And then maybe think of why that could also have some shortcomings. what would be interesting about this idea, as opposed to, because so far we said that from our index, the index points to the actual physical location of the record. From the index, I find the read, and looking at the read, I can physically find in which page the actual record lies. Now we're saying, well, the other way of thinking about this is opposed to have that reference, why don't I just put the entire record itself into the index next to its key? And if there are a set of records that are relevant to that, well, we can just put all of those records contiguously, one next to another. So why is this beneficial? How would it help me be able to having this also called the index organized file? Why is that beneficial to not put the read? First of all, let me know if you have any, if it's clear, the question. So from a reference, from our index, I could, for each key, I could have a pointer, a reference ID to the physical location of the record. I can just keep a pointer to that record, or I could just store the record itself right inside the index. So what would be one benefit of doing that?
It could speed up accessing the data you're looking for.
Sure, absolutely. I don't need to because given a read, that's like in the form of an indirection. So now I have to follow that reference, and however that reference is computed, I need to do another lookup from that point on to somewhere else where the actual record is. But as you said, if the record is right in the index, then I can save that. What other benefits could it have? That's an important one, but what else? So one other benefit is that if I'm using a tree structure, then essentially I'm going to get a sorted file, and the actual records are going to be in a sorted order. So that's one way of creating a sorted file using an index. And the index structure, for example, trees already kind of manage. If you were to insert to a page that is already full, they have mechanism to split it and so forth. So essentially gives me a way of maintaining a sorted file. Now, a limitation with this, the number one limitation, major limitation for it, is that if I were to actually store the record entirely into my index, then my index becomes much larger, as opposed to if my index only had reads. The other challenge of this, of course, is I can no longer have the records in the table. So this is going to be the way I store my records. And otherwise, I'm going to have duplicate data. So then if I need to update stuff, I need to update it in the index, and then I need to go change the record. Also in a file, it becomes a lot more complicated. It also becomes a little bit complicated in terms of, now if I want to have multiple indexes on a file, now what I'm end up potentially could end up in a situation that other indexes are pointing to this index. So I have indexes over indexes. Again, causes additional complication. But again, it does provide a nice way of maintaining a sorted file. So that's an important benefit. The other alternative is, as we said, so these are kind of summary of what I just said. The other alternative is basically I have a key and just maintain a set of reads. So just a key and pointers, and 2 and 3 are relatively the same. So the idea again is just have a key, a set of reads. The other one is have the key, but then just put the entire record there. So 2 basic ideas. I could just keep the entire record in my table, or I could just have grids. And you can think of it that these are the two main alternatives or two main design. Any question on that?
Professor?
Yes.
So how the files end up being sorted? That's the part I didn't understand. You said that by having the first method, then we would have sorted files or sorted entries?
Yeah, because if I have a tree structure, the trees, for a tree, everything is sorted. Because the tree has a key 1, has H1, H2, H3, H4, H5, H6, and so forth. So, and if my leaf pages are also, so my leaf pages are all going to be sorted, and leaf pages are just going to be sorted. They're nothing special about it. They're just a bunch of files. And so I could essentially get into a situation where I have just a set of sorted files. I have one picture. Let me see, maybe that helps. So yeah, so this might be helpful is that, so I have an index, and this is, for example, this leaf page, this is H21, this is H22, this is H36. So all the H21 are here, all the H22 are here, all H23 are here. So essentially I'm going to have a sorted file. So because and then these are all linked. So this becomes a sorted file. A sorted file consists of a set of pages. A file is always consists of a set of pages, and these are a set of pages that are sorted, and I have pointer from one to the next. So essentially, it is a sorted file.
Okay, thank you.
You're welcome. Any other question? And that's an important question.
So for a database with records that have multiple fields like age, name, major, we would have an index. We would possibly have an index for each of these fields to be able to find certain records.
Yes, exactly, and we're going to look at that. We're going to have a couple of examples on that. Yes, precisely. So you could define multiple indexes, and you could define composite indexes in the sense that an index is just an age, but you could also have an index that is both on age and salary. And one task of the database administrator or the database designer is to figure out what indexes to build to speed up the queries. But also, the more indexes we have, that the more difficult our update, or the more complicated or costlier our update is going to be, again, going back to that trade-off situation that we have been referencing. And on that topic, we also have two types of indexes. We call it primary and secondary. If the search key of the index is also the primary key of the table, and then the primary key of the table, again, it's the key of the relation, is the key of the table. So if you have a student table, and if you have a student ID, or a student table could have student ID, and the student ID is unique. Each student is identified by student ID, so that becomes the key of the relation, and you can think of it, that becomes the primary key. A single relation could also have multiple keys. We could also maintain a social security of the student. So that's also, we know it's unique. And so that it is a key of the relation, but it's not the primary key. We usually have only a single primary key. We have multiple unique keys for the table, but we only designate one as the primary key. Now, if this index is built on top of the primary key, is the index on top of the student ID, then we call that a primary index. But if the index is built on top of the age column, which is many students have the same age, so it's not a unique column, then we call it a secondary index. Just terminology. These are common terminology. Primary key, talk about primary key, we call primary indexes and secondary indexes. Primary indexes are the one on the key, on the primary key of the table. Secondary is everything else, basically. Any other index beside the index that is built on top of primary key is called secondary. So just a terminology that is used in the field. And then the indexes could also be clustered versus or unclustered. And that one I think is easier. I'm going to talk about this. We'll show you the figure, so that's easier to see with the figure. And whether it's primary key or a secondary key, we could have different alternative. Of course, in practice, we could only have one alternative one because we don't want to store the record multiple times, the entire record multiple times, and probably also makes much more sense to have if we were to do alternative one index organized file to do it for the primary key. So it's not necessary to do that, but it's probably a logical thing to do. And since we can only have one kind, that means the relation can only be sorted in one way. And that's typically true, is that you cannot have the same relation sorted in multiple ways, because that implies you have multiple copies of that relation. There's nothing wrong with having multiple copies of it. It is possible, but typically it's not something that is supported by sort of databases, because it causes a lot of other complication, and it also causes additional storage because you have to record the data multiple times, and it also makes the updates more expensive. So we only have one single order, so usually we only have one alternative one type of index, because well, we want to copy data, we want to store the data once. That's what sort of traditional databases do. Doesn't mean that that's the only way that needs to be done. In fact, when we talk about like blockchain and sort of we talk about that space, you really emphasize on the need of replication, meaning that we want to have many copies of the data. In case one copy failed, we want to have potentially tens or hundreds of other copies available, perhaps even globally. So that's a choice that could be different in sort of blockchain setting. So now, what's the difference between clustered and unclustered? Is that kind of coming back to this figure, is that this is, so we call something as clustered, is that, let's say this is an index on age, and this is the entry for age 21, this is entry for age 22, and this is entry for age 23, okay? But what we see here, the entry for age 21, either they're all on the same page or they are on the page next to it. Entry for page 22, they're all in the same page or perhaps on a page next to it. So we call this clustered when the order in which the actual physical records are stored corresponds to the entries into the index. Alternatively, if I had my data entries, I would call it unclustered. If for age 21, one record is in this page, one record is in that page, and maybe one record is in the other page, if it's all over the place, it's unclustered. But if they're all in the same place, they're called clustered. And essentially here, I'm also getting a sorted file. Even if I don't store the record, even if I don't store the actual record in the index itself, if I have a clustered index, by design, I am going to get, or by construction, I'm kind of going to get a sort of files, because all the records on the file, the data record on the file, following almost the same order as in the index. So this is called clustered. Essentially gives me a sorted file. This is unclustered. That means they're all over the place. And so there is no, so this is now the data record, at least are not sorted based on the search key here. But the data records are almost sorted based on the search key of this index. So this is called clustered index. This is called unclustered index. This is sort of an important topic, or it's not a difficult one, but it's an important one that, so I want to make sure to sort of pause to make sure everybody understands it. So this is having a cluster index allows me to essentially implement a way of doing sorted file. And could I have multiple clustered index? Is it possible that I have multiple cluster index for the same table? Or is it only one cluster index that I can have? And why?
I'd say only one clustered index, because like if you're sorting by age, that's different than sorting by name.
Exactly, because at the end of it, these can only be in one order. So if it's by its age, then only my age index becomes clustered. All the other indexes become unclustered. So that's precisely. So now the other question is, how does this help me, this cluster index help me to create this notion of sorted file? Any insight onto that? Why does it give me sorted files at the end? Because I said I can just sort my data, and once I have sort my data, and then I can just create like a heap file, just push them into the file one after another, or push them into pages. So I sort my data, and then I start inserting into the pages. And since the data is sorted, my insertion order is sorted, then once I'm done, I get a set of pages that are sorted. So that's, I can easily create sorted files. But then if I need to insert something in the middle, or I need to remove things, then I need to reshuffle, and potentially it's very expensive. But with these kind of clustered indexes, what I could do is that when I add age 21, so I create a page, and initially it's possible that age 21 and 22 and 23, they could potentially all be in the same page. And I could fit all of them in the same page. But what I could do is that when I create a page, I always leave part of it as empty space. So I could, a tunable parameter, 30% of a page that I create is always, I keep it empty. I don't fill it up. So when I'm doing 21, I only fill up 70% of it, leave some empty, and then I go to the next page and start putting 21, and again, try to keep 30% of it empty. And this is the way that I'm going to construct all my my index, and this is the way I'm going to store my data records. So now in future, if I need to insert a new record of 21, then I have some space available to me. So that allows me to much easier to kind of utilize that empty space in future to avoid a lot of reshuffling. So that's also another technique that is kind of used. Pretty common use in most relational systems. But again, the notion of clustered versus unclustered. The clustered, the entries in the leaf pages correspond to the order of the entries on the data files or on the data records. Unclustered, well, that relationship does not hold. And usually this is a best effort. It's not has to be precise. But overall, we get a clustering ratio. So the index is 97% or 98% kind of clustered. For most data entry, that relationship holds. Okay. So again, is that clear? The cluster, unclustered? Because I just see a comment saying what is clustered and what is unclustered.
I have a quick question, just conceptually.
Sure.
So, and this is how stuff is stored on record. So this is on actual hard disk, not in dynamic memory, right?
So again, instead of thinking about dynamic memory or talking about hard disk, think about the conceptualization that I gave you. Records are put into pages, and for now, just think about row base. Records are put into the pages, and you can think of a page as an array. Now, an array of bytes. Now, that array of bytes could be on disk. That array of bytes could be in memory.
Okay. So then for this clustered concept, like this is something you really only want to employ if you're searching on that index, or like if you're searching on a specific index a lot, right? Like if it's clustered based on age and you're searching predominantly by name, then it's not as effective a method.
If it's not an effective method if you need to do range queries.
Right. Okay.
So if I want to get all the names who starts with the letter A and ends with letter D, then that's not effective for names. But if your search query, for example, for age, give me all the ages between 22 to 25, then if you have a clustered index is more effective because the data records that you're going to access are going to be in sequential order essentially, versus because if, let's say from 22 to 25, 22 is here and 25 ends here. So that means I just need to see these pages, and I could potentially see these in a sequential access. And I only, even if there was no sequential access, these records will maybe span only 3 pages. So I only need to look at 3 pages. But versus if it was all over the place, from the index, I figure out which records I need to see. But when I go to the actual data records, one of them is here, one of them is here, one of them is there, one of them is there. So I end up actually reading all the pages. Versus when it's clustered, I only read those pages that are relevant to my search query. When it's not clustered, I could, because the records could be all over the place. 23, even if I was looking for record 23, and if there's a lot of 23, every page could have a record of a 23. Then I have to look at everyone. Here, all the 23 records are in 1 or 2 pages, are all sort of concentrated in a set of pages. So that makes it sorted, and that makes it clustered, and that makes it much more effective to extract it.
So then we would potentially, and I think Kevin or another student asked this earlier, we would have multiple clustered indices for the same set of data files.
Well, again, you can't do that. So that becomes complicated, because if you have multiple cluster indices, that means your data needs to be essentially, because this is another way of thinking about it, is the data is kind of sorted by age. Since the data is sorted by age, all the record of age are concentrated in a few pages. On this side, the data is not sorted by age, so the age is all over the place. And typically, you would only be, if you sort your data by age, it's not going to be sorted by name, and it's not going to be sorted by social security. In order to sort the data by social security is a different order. So typically, you would only have one index, that is, your data file is going to be sorted in one order. That means only one of your indexes could be clustered, unless you maintain multiple copies of the data. If you only have one copy of the data, it's going to be sorted in one way. And if you have an index that is on the sort entry, then that index will be clustered. Does that make sense? Any other question? Queuing, is that now make sense?
Yeah.
Okay, perfect. All right. So that's cluster versus unclustered. Okay, we have a few more minutes. So now, kind of these questions that it was kind of asked is so far already. So then, depending on which relation do we access more often, or which attribute we access more often, and more kind of sort of, we haven't really talked about selection, join, or kind of more advanced operation, SQL operation. Depending on those, then we need to decide what indexes to build. And also depending on how selective a condition is. And selective condition, selectivity in the database, it means if a query or a condition is selective, means it returns very few elements. If it's low selective, it returns everything. So high selective is very selective. It only returns a very few. It's low selective, well, just returns everything. So if everybody has an age 25 in this, if everybody's 22 in this class, and I run a query, say, give me everybody of age 22, this is going to be a very low selective because I essentially could get the entire class. But if I ask maybe who's of age 17, for that is not going to be as selective because maybe only one of you is 17 and majority are older. So the selectivity affects whether the index is useful or whether using an index is useful for the query. And of course, the other part is that we got to look at the query that we wanted to speed up to figure out what indexes to build. But every time we build an index, we're also going to make our update harder because now we have to update all these indices. So there's more work to be done. So again, the trade-off continues. The design trade-off in databases continues for that reason. And so again, the choice of indexes. Let's kind of look at a couple of examples since we have only a few minutes. I think just looking at a couple of examples probably helps. So this is, we haven't talked about query, but this is a pretty simple query. It doesn't have much semantic. It's just select a number from the employee table, the department number from the employee table where the employee has the age of 40. So in order to answer a query like that, give me everybody with the age greater than 40. So we already talked about basic hash table doesn't work because hash tables for equality. So if you don't have an equality condition, then we probably have to use some form of either a tree or we could potentially use R hash. And it also, so that tells us this is probably good to use tree. It also says we can ask the question of the selected. Is it the case that everybody in the department is older than 40? If everybody is older than the 40, then we probably don't even need index. Might as well just scan the relation. And also the other one is whether the index is clustered or not. If there are some people who are above 40, not everybody, so it still makes sense to use an index. But if the index is not clustered, meaning that those people are going to be all over the place on the pages on the file, so that means I end up going to have to look at every single pages, then again, the index, using an index becomes, again, not that effective. So if it's low selectivity, if it's a high selectivity, then the index is effective. If it's a low selectivity, but at least the index is clustered, that I can limit the number of pages that I need to access, again, the index, using an index could be effective. So now this is another one, give me employee who, the hobby of the employee is to collect stamps. So again, I could use a hash table, it might be useful, and the clustering on a hobby could also be helpful, especially if there's a lot of employees who have a hobby of the stamp. That could be helpful, but if this is a very highly selective and only very few people like that hobby, then it doesn't really matter. The index will be useful even if it's not clustered. So a couple of more examples here. So I could have a table, data records, name, age, salary, and I could have different kind of indexes built. I could build an index on salary. For age 10, point to the record 10. For 20, point to the record 20. I could build an index on it on age only, again. I could build an index, a composite index that is age and salary. So it's sorted by 11. 80, the salary, or 12. So it has all the 12. And then the second is sorted. So we get two sort levels. So the first is sorted by age. Then for all the 12, it's sorted by salary. So that's what it means to have an index age by salary. I could also have the composite index in the reverse order. So salary by age. So that means my initial sort order is first by salary. And if the salaries are the same, for those with a similar salary, then I sorted with with age as a secondary sort order. So again, you could have many indexes. Now you ask whether there are some query that helps me if I only have the age salary. Then there are some queries that help me if I have the salary index. There's some queries that help me if I have composite, and whether these are range query, whether these are equality queries, whether do I need to have a clustered index, and sort of the things goes on and on. But at the end of the day, my data records can only be sorted by one way, and here they are sorted by name. So none of these indexes are actually going to be clustered because none of them are an index that starts by name. So I will have 4 indexes that are unclustered, and you can see it too. The arrows are kind of, for the most part, are kind of all over the place. Although there is for the salary, I guess there's a bit of a sort order, 10, 20, well, not really. So they're all kind of unclustered, just because the order in which the main relation is ordered by does not match the order in any of the indexes. Thereby, all the indexes just becomes unclustered. If I had also an index on name, then that index would have been clustered because it does follow the same order of the main relation, of the main table. Any questions? And I think this is probably a good point to stop. And we could next time just maybe spend a few minutes, look at a couple of cases, queries that will benefit one index over the other. So that's something we can do next week or on Thursday. But I think that's kind of a good point to pause for today.
So
Go on.
if another column somehow correlated to the column that the index was using, would that be considered clustered?
So again, the question of the clustering is kind of if the order in the you can think of the order of the sort of the data items or the leaf pages correlates with the order of the actual orders of the data records on pages. If there is a correlation, we call it clustered. If there's no correlation, it's just unclustered. In this cases, sorry?
I was saying, like, if 2 columns were correlated, could it theoretically be clustered by more than 1 column?
Yes, exactly. That's a really important point. Exactly. Okay. So that's a really important point, is that in fact, in fact, some of the work I did when I was at IBM is to identify a set of correlated columns and sort based on the correlated column to try to maximize the number of clustered indexes. So that's an essential, that's really important, to try to identify correlated item and try to maximize that set. Of course, there's not so much you can do, it's limited, but that's really important. That's a very good insight. And it is possible. It is possible that you have correlated columns.
Thank you.
I mean, just one potential correlation that you could easily find is that the salary is correlated typically with age. So typically when you have more experience in a company, you tend to have higher salary. So there is a correlation. So natural correlation does happen. But of course, there's no correlation between your name and salary, although there are things that you find that there are correlation with ethnic background and salary just because of biases. So there are bias correlation does exist, and you do find it. Or maybe, for example, still I think males will make more money than females. And so there is that bias that exists. And so there could be a correlation in the data just because of that unwanted bias is there. But so the correlation is there, just strictly looking at the data. So the correlation does exist. It can be found, but it's limited. Very limited kind of correlation are typically there as far as the sort order concerns.
So to be clear, the indexes are mostly used for column-based storing of data, right? Or is it also for row-based?
Indexes typically actually becomes more effective for row-based because, yeah, it becomes more effective for row-based just because if my scan operations becomes more efficient, then the need of indexes reduces. If my scan operation is not as efficient, then indexes becomes more useful. And the column-based, because I can only sort of really target exactly the data that I want to read, my scan becomes more efficient. And if my scan is more efficient, then there's a less need for having indexes.
Oh, right. Okay. And by scan, you mean like you have a certain range for your query of the data you want to retrieve, right?
Scan means just kind of just read everything, either just read partially or just go ahead and read the data, as opposed to do an index lookup and figure out what to read. Just kind of a brute force read of everything.
Okay, that makes sense. Thank you.
You're welcome. And so I think after milestone 1, a lot of these concepts I think becomes really, I think starts, you're going to get a much better handle on it, because we're going to look at it. You're going to build this, what's in the middle, and optionally some indexes as well. And of course, we're going to have row. We're not going to have row, we're going to have column based. And so we're going to look at all of these to kind of build it together. So. All right, everybody, have a wonderful day, and I'll be around if you still have a question for me. Thank you, everyone.